Hey guys, so in today's video we are going to cover the other three types of chemical reactions. So just to recap, at this point we've covered single replacement reactions and double replacement reactions. In this video we're going to be looking at what is called synthesis reactions, decomposition reactions, and combustion reactions. So let's go ahead and get started with our synthesis reactions. So some characteristics of a synthesis reaction is the idea that you're going to have two or more reactants forming a single product. So multiple reactants are going to come together to form just one product, one compound at the end. And here in the bottom right hand corner we have an example of a synthesis reaction where we're taking some potassium and we're taking some chlorine gas and we're combining them together to create potassium chloride. So let's take a look at some example problems for synthesis reactions. So again, like we saw on the last slide, in synthesis reactions, we're going to have multiple reactants forming a single product. So you have to think about how would the reactants that I'm given combine to form a product. So in the first equation here, we've got aluminum metal reacting with oxygen gas. And so when aluminum reacts with oxygen, we know that aluminum has a charge of +3 and oxygen has a charge of -2. So when those two elements are going to combine, they're going to end up forming aluminum oxide. And then we have to think back to our video about predicting states of matter. So aluminum oxide, because it has a metal and a nonmetal, is an ionic compound. And we know that ionic compounds could be aqueous if there's water present, or they could be solid if there's not water present. So when we look at this chemical equation here, we see that there is no water present, so we predict that this aluminum oxide is going to be a solid. Now I'm not done quite yet. I'm still missing one step, and that step is balancing. So when you take a look at your chemical equation, you want to make sure after you've predicted the products that you go ahead and balance the equation. So I'm going to start by balancing oxygen first. So I see that I've got 2 oxygens on the reactant side and 3 oxygens on the product side. So I'm going to put a 2 in front of the aluminum oxide, and I'm going to put a 3 in front of the oxygen. So that gives me 6 oxygens on both sides, which means I need to put a 4 in front of the aluminum on the reactant side. So let's go ahead and do one more, and then I'll have you do the third one on your own. So in this one, we've got solid sodium, so Na, that's a solid, reacting with chlorine gas. Now remember, chlorine is diatomic, so it's going to be Cl2. And when I think about how chlorine and sodium are going to bond, remember sodium has a charge of +1, chlorine has a charge of -1. So when they combine, they're going to form sodium chloride. And then when we're thinking about the state of matter, we know sodium chloride is an ionic compound because it's got a metal and a nonmetal, but there is no water present, so we're going to predict that this sodium chloride is going to be a solid. And then my last step, just like in the first problem, I have to go through and balance it. So I'm going to start by looking at chlorine here. So on the reactant side, I have 2 chlorines. On the product side, I have just 1. So I'm going to add a coefficient of 2 in front of the sodium chloride. So now chlorine's balanced, but now I need to add a coefficient of 2 in front of sodium to balance the sodium. So I want you to go ahead and do the last problem on your own and then check your answers. So our next type of chemical reaction we're going to be talking about is a decomposition reaction. And decomposition reactions are really kind of opposite of synthesis reactions. So in a decomposition reaction, you're going to have a single reactant that's going to break down into simpler, smaller substances. So we've got one reactant with multiple products in this type of reaction. And a good example of a decomposition reaction is actually the decomposition of water. So we can take water as a liquid and we can decompose it into hydrogen gas and oxygen gas. And we do this through a process shown below called electrolysis. And what electrolysis is it's the idea of using a current to actually break apart particles. And another kind of cool or another unique characteristic of decomposition reactions is that they usually require some form of heat or energy in order to help you decompose whatever reactant you're starting with. So let's take a look at some decomposition practice problems. So remember, in decomposition problems, you are taking whatever reactant you have and you're breaking it down into its pieces. So when we take a look at the first one, we've got potassium bromide. So we have to think about what would be the pieces that potassium bromide would break down into. And so the first thing we're going to see is it's going to break down into some solid potassium, and it's going to break down into bromine. And remember, you have to look at your periodic table in order to figure out the state of matter for individual elements. When we look at the periodic table, we see that potassium is in black font, meaning that it's going to be a solid. Bromine is in blue font, meaning it is going to be a liquid. And then just like we did in our synthesis reactions, we need to go back and balance it. So we're going to start by balancing bromine first. On the product side, we see we have 2 bromines. On the reactant side, we see that we have 1. So we're going to add a coefficient of 2 to balance our bromine. But then now we've unbalanced the potassium. I see that I have 2 on the reactant side, so I need to add a coefficient of 2 on the product side as well. So let's take a look at the next one together. So in this problem, we see that there is a polyatomic ion present here. And so anytime there's a polyatomic ion, the products are actually going to be predicted for you. So I would give you that in this barium carbonate compound, it's going to break down into barium oxide as a solid and carbon dioxide gas. All I would ask is that you would then need to go through and balance it. So if we take a look at this example problem here, you would see that it is already balanced. So there would be nothing for you to do for that problem. But again, anytime you're doing a decomposition reaction and your reactant has a poly in it, the products would be given to you already because it's too hard for you guys to be able to predict what that poly would break down into. So now I want you guys to go ahead and do the next 2 on your own and then check your answers. So the last type of a chemical reaction is what we call a combustion reaction. In combustion reactions, you're always going to have what we call a hydrocarbon, so something made out of hydrogen and carbon, reacting in oxygen or being burnt in oxygen, and you're always going to produce carbon dioxide and water as your products. So that's going to be kind of our indicator that we're looking at a combustion reaction when we have carbon dioxide and water as our products. For those phases of matter, oxygen, as we know from our periodic table, is always going to be a gas. Carbon dioxide and water are also going to be gases because remember, combustion is going to be involving the burning of the hydrocarbon in oxygen, and so that water won't be able to remain a liquid, it'll become water vapor. And then the state of matter of the hydrocarbon itself could be a gas or a liquid, but that state of matter will always be given to you. All right, guys, so here we're going to look at some practice problems with balancing our combustion reactions. So the first thing I want to ask you guys are, what are the products of a combustion reaction always going to be? So hopefully you remember that the products are always going to be carbon dioxide and water. So we can go ahead and fill those in for both of the examples below. And now I want to ask you, what phase of matter are those carbon dioxide and water molecules always going to be when we're talking about them in relation to combustion reactions? Hopefully you remember that they're always going to be gases, because remember, combustion reactions involve burning the hydrocarbon in the presence of oxygen. So because of that heat, that water isn't going to be able to remain a liquid, it's going to become water vapor. So now that we've predicted our products, we need to go through and balance our reactions. So I'm going to give you a couple of pointers when you're balancing combustion reactions. So the first pointer I'm going to give you is that you always want to start by balancing carbon first. So in our first example, we see that we've got 3 carbons on the reactant side and 1 carbon on the product side. So I'm going to add a coefficient of 3 to balance the carbons. Your next step is going to be balancing hydrogen second. So when I look at the hydrogens from my hydrocarbon, I see that I have 8 hydrogens on the reactant side and 2 hydrogens on the product side. So I'm going to add a coefficient of 4 in front of the water molecule. And now we have to balance our oxygens last. So when we go to balance oxygen, we have to remember that we are going to be looking at oxygen in 2 of the products and balancing oxygen in 2 products on one side versus 1 reactant. So I have to add together the amount of oxygens that I have on the product side. So remember, the coefficient is going to be multiplied by the subscript. So in this carbon dioxide, I have a total of 6 oxygens, and I'm adding them to 4 oxygens from the water, which gives me a total of 10. So I need to think about what number would go in front of the oxygen that would give me 10 oxygen atoms. And that number is going to be 5, because 5 times 2 is 10. So when we're thinking about balancing our oxygen, so in this first problem, it was a little bit easier than what we're going to be looking at in our second example. So let's go ahead and walk through the steps of balancing our second example together. So again, start with carbon. So in the hydrocarbon, we see we have 10 carbons. In carbon dioxide, we see we have 1, so we're going to add a coefficient of 10. In our hydrocarbon, we see that we have 22 hydrogens here, whereas in our water molecule, we have 2, so we're going to add a coefficient of 11. And now we're on our step of balancing the oxygen. So when we're balancing the oxygen here, remember we have to add together the oxygens we have in the carbon dioxide and the water molecules. So in the carbon dioxide, we have a total of 20 oxygen molecules, or 20 oxygen atoms, sorry, and we're adding it to 11 oxygen atoms from the water, which gives me a total of 31 oxygen atoms. There is not an easy way or an easy number for me to put in front of this oxygen that would give me 31. So right now I know I have 31 over 2 oxygens, or 15.5 oxygens. So we're going to add a 4th step to our checklist, and we're only doing this step, so I'm going to draw a line, because you're only going to do this step if you end up with a weird number in front of the oxygen, where you have 15.5 or 31 over 2. So when that happens, we can't really have half of a molecule. So we need to go ahead and we're going to double all the coefficients written and then try balancing oxygen again. So if we go through and double all of our coefficients, remember in front of the hydrocarbon right now there's a 1, so I'm going to go ahead and put a 2 there because I'm going to double it. I'm going to double 10 to 20 and 11 to 22. So that's then going to change my oxygen count on the product side. So now I'm going to have 40 oxygens from the carbon dioxide plus 22 oxygens from the water, which is going to give me a total of 62 oxygens on the product side. So when I think about what number is going to go in front of the oxygen to give me 62, that number is now going to be 31. So that it's a little bit more complicated, but if you get stuck, use this step number 4 to see if you can balance your oxygens. Anything that you can do to check and see whether or not your coefficients are correct, because these coefficients do seem high compared to the first problem on the page. But you want to see if all of the coefficients are divisible by a single number, if they can all be reduced by the same number. If they can, then you need to reduce them down. If they can't, then you know that you have the correct answer. And that is it for our 5 types of reactions.